we're going to go over mass spectrometers now. I know you're probably asking what the heck is a mass spectrometer. It's the thing in front of you, or at least this is a diagram of a mass spectrometer. What it's used for is to accelerate particles and then bend them in this third chamber here, because that is going to help us know their mass, their charge, and help us identify the nature of the particle. So that's what we use mass spectrometers for. So there's three main chambers in the mass spectrometer. First one right here is an ion generator and acceleration chamber. So that's really important to know that this one is the acceleration chamber. Secondly, here we have the velocity selection chamber. So that is where it just has constant velocity is going to go through, and so only things with certain velocities can go through. And then we have our separation chamber. So we see these two beams separating into these two different paths. So that's why it's called the separation chamber, because obviously it's separating the different types of ions into different paths, and we'll go over how that's working in a bit. Okay, but let's start from the beginning, the acceleration chamber. All right, so this is the first one right here. That's the acceleration chamber. And so what's happening is that we have ions being produced in this chamber. Specifically, we're producing positive ions. Okay, so what we have is we have an ionizer here. It's going to shoot electrons and get the electrons on the atoms here loose, and then the electrons are going to go here, and the positive ions are then going to go here. The reason being is because we're going to set up these parallel plates to have different charges. All right, so we're going to strip the electrons to produce the ion. And then, of course, our electrons are attracted to the positive plate. Which means we have to make this plate right here the positive one, and this one the negative, so then our ions can be attracted to the negative plate. Well, how do we do that? We set up a battery on these two parallel plates. See, we have one plate there, we have one plate there. So we have to set up a battery here in order to get this to have a positive and negative terminal. So how do we set up this battery? Well, if we want the plate on the left to be the positive plate, that has to have the longer line there, of course. I'm really exaggerating this. And then if we want the plate on the right-hand side to be negative, then we have our shorter line there. And so that's just telling us that there's a battery there, with this side being positive, making this plate positive because the positives are going to go down there, and this side being negative because the negatives are going to go down there. Okay, so there we go. We know then, therefore, that these ions are going to be attracted to the negative plate and are going to accelerate towards it because they have an electric force exerted on them towards the negative plate. So that's why it's called the acceleration chamber, of course, because it's going to accelerate. So believe it or not, you guys already know how to do the math for this, but just in case you don't, let me help you out here. So we can assume that all my potential energy is being converted into kinetic energy. So the potential energy as the ions are just coming out of the sample, and as they're being sped up towards the negative plate, we know all that potential energy, due to the fact that it's an electric field, is being converted into kinetic energy. And as it reaches that negative plate, all that potential energy has been converted into kinetic energy. Okay, so really our potential energy in this situation is charge times the voltage, so Q times V, and that should equal to our change in kinetic energy, which would be 1/2 mvf, so our final velocity, minus our 1/2 mvi, our initial velocity, so that's our final kinetic energy minus our initial kinetic energy. A lot of the time, the initial kinetic energy is going to be 0, but just in case it's not, here is how you would solve for the final velocity in this case. Okay, so there is our equation for the final velocity, or at least the velocity once it reaches this velocity selection chamber. So depending on what kind of charge you have, depending on what the mass of the thing is you have, we can find our final velocity. Now, what if mass is the thing that we're trying to find? Well, then we find our final velocity here by other means, by recording it, and then we can go ahead and find our mass or our charge from there. All right, let's go over the next chamber, and that is our velocity selection chamber. So that's this guy right there. That's not supposed to have a 1. That's supposed to be a 2 because that is our second chamber. So this is the velocity selection chamber. I'm just going to call it velocity chamber because, laziness. Anyways, what's going on in this situation is we have mutually perpendicular magnetic and electric fields. So here, to get them mutually perpendicular, well, you got to do a little bit of reasoning. So we have to know, first of all, which direction our positive and negative plates are going to be, and then depending on that, we can figure out what direction the magnetic field is going to be. Because if we want all these ions to go straight through here like this, we have to have the perfect voltage and the perfect magnetic field strength in there in order for them to go that direction. If they come in here and do this or that, those aren't the type of particles we really want to study. And so that's why it's called the selection chamber, is because it's selecting only certain particles to let them go through. Some of them will go up or down, either being influenced by the electric field or the magnetic field more than the other. But what we want is ones that are perfectly affected by each. So we want positive ions where the electric force going upwards is equal and opposite to the magnetic force going downwards. Okay? So let's just say in this situation that I had a battery tied to this that looked something like this. And I'm going to do this and then this. So what does that tell us? That means that this is the positive side, right? So our positive plate is going to be this one at the bottom because that's where it's connected to. And this is our negative terminal. So therefore, this is going to be our negative plate because, of course, that negative terminal is connected to that top plate. Okay, so if this is what's going on, then in this case, our electric force is certainly upwards because this is a positive ion. So I know the electric force will need to go upwards. So what I need to do is I need to create a magnetic field in order for there to be a force that's equal and opposite downwards. So how the heck are we going to do that? Well, we need to use our third hand rule to figure out the direction of the magnetic field. So you're going to use your right hand because it's a positive ion. Your thumb should be pointing to the right. And then we know that we want the force to be going south or to the bottom of the page here. So therefore, if my magnetic force is going south like this, therefore my magnetic field should be going out of the page. And again, if you just orient your hand so right thumb is pointing to the right, your palm is pointing downwards to the bottom of the page, you'll see that your fingers are coming out of the page, which is exactly what you need, and that's telling you that your magnetic field is going to be out of the page. So that's an example of a question you could be asked about which direction is the magnetic force going to be, and or which direction will the magnetic field be. Okay, so what we can do here is we can determine our electric force based on the plate charge. Because in a mass spectrometer, that's what you control, right? You're controlling what voltage the plates are going to have between them and the distance between them as well. So we can determine the electric force based on the plate charge, and then we can determine the magnetic force with the third hand rule, or at least the direction of it, right? And then here, since we have two equal and opposite forces, and we know that since they're equal and opposite, this is just going to have a nice constant velocity through this chamber. That's why it's a velocity selection chamber, not an acceleration selection chamber. What does that mean? It means that the net force is 0 because we don't have any acceleration. So when we set up Newton's second law here, the net force is equal to mass times acceleration, we know acceleration is 0 because we just want to select a certain constant velocity. And that is why that's so important, that the electric force and magnetic force are equal and opposite, because that makes our life way easier. So we know that electric force minus your magnetic force should equal to 0. Now we do have, so that means our electric force is equal to magnetic force. Of course, we do have equations for electric force and magnetic force. One of them we have for electric force is Q times the electric field. So that's the force that a small charge will experience in a big electric field. And the only equation that we can use for magnetic force here is QVB. Remember, this V being velocity, not voltage. Very, very important. Look, we have Q on both sides. So those can go ahead and cancel out. And then we can solve for whatever we need to. Maybe this is where we solve for the velocity, and then we can go back a step and solve for mass or something like that. Okay? So what we get is our velocity is equal to the electric field divided by the magnetic field. And there you go. That's how we can figure out what velocity is required through the velocity selection chamber. Really, really important. All right, let's move on to the third segment. So that's this guy right here, this ion separation chamber. So what's happening here is we only have a magnetic field, okay? So this is our separation chamber. So it's only a magnetic field. Okay, so just to review, this is something a lot of people have a hard time with. Which is which is which? So remember, my first chamber is only an electric field. My second chamber is an electric and magnetic field. Has both of them. And then here, my third chamber is only a magnetic field. And this magnetic field is different from the previous one, just like this electric field is different from the previous ones. So it's not the same electric field in chamber 1 and 2. It's not the same magnetic field in chamber 2 and 3. They're completely different. So what's going to happen here is uniform circular motion. Everybody's favorite part of Physics 20. Aren't you guys so excited? Because what's happening, we know that if if you have a moving charge through a magnetic field, there's a force on it. Well, guess what? So at first, when the positive ion here comes through, it's going to be forced down. And guess what? It actually starts to move down. And then when it's right there, guess which direction the force is? It's right there. And guess when it's right here, which direction is the force? Right here. And here the force is like that. And here the force is like that. So what's happening is as the charged particle changes direction, so does the direction of the force. And it actually starts going in this nice circular motion. Got this nice circular radius, just like that. So we do have to go back to our circular motion stuff from Physics 20, which I know you guys are just so excited about. So depending on whether it has a smaller trajectory, a tighter circle, or takes a bigger circular path, that's actually going to depend on the mass, and specifically the mass to charge ratio, which is what we're going to be trying to find here. Okay, so remember, this is where we have uniform circular motion. And of course, we're going to determine the magnetic field with the third hand rule. Okay, so what's happening is we know that our force of the centripetal motion is equal to mass times centripetal acceleration. What is the only force acting in this third chamber? It's just the magnetic force. We're talking about things that are so little we don't really have to worry about gravity here, okay? They still have a mass, we just don't need to account for gravity. So the only force that is contributing to the centripetal force is the magnetic force. And of course, we know that's equal to mass times centripetal acceleration. So if you guys don't remember from Physics 20, centripetal acceleration is v squared over r, but then I'll just write the whole m in the v squared over r. And there we go. That is what our magnetic force is going to equal to, is our mass times our centripetal acceleration, because our magnetic force is our entire net centripetal force here. So what's our magnetic force equal to always in this kind of situation when we just have a charged particle moving? It's QVB. That's equal to mv squared over r. So let's see what we can do, because again, what we want to find is the charge to mass ratio. So we see that we have v here and v squared here, so those can cancel out, still leaving me with 1v there. And if I want my charge to mass ratio, that is q over m. That's what a charge to mass ratio is. So of course, I'm just going to divide both sides by b, divide both sides by m, and I will get, at the end, its velocity divided by the magnetic field times its radius. And of course, that's the radius that it moves in up here. So this is your charge to mass ratio. And as you see, the mass is directly proportional to the radius, because they're both on the bottom of the fraction on either side of the equal sign. So what does that mean? It means that the larger your mass is, what happens to your radius? Larger radius. So this guy right here, beam 2, probably has a bigger mass. This guy probably has the smaller mass. Okay? So we like to solve for charge to mass ratio because likely all of these ions will have the same charge, so we just want to know how that relates to their mass. One more note I have for you here is that we can figure out the direction of the magnetic field in this third chamber here, because as we can see, we have our charged particle, our positively charged particle here, going to the right. And then we know that the force on it is going south or to the bottom of the page. So we can use our third hand rule again, where my thumb is going to be pointing to the right, and then your palm is going to be pointing downwards or pushing downwards. And so when you do that with your right hand, you see that your fingers are coming out of the page. Right? So in order for my thumb to be pointing right and my right palm to be kind of going downwards or pushing downwards, I know my fingers are going to be coming out of the page. So that means that my magnetic field in this velocity selection chamber, or sorry, not the velocity selection chamber, in this bending ion separation chamber is going out of the page. So we draw our little dots here, right? That's like the arrowhead, to tell us that the magnetic field here is coming out of the page. Now again, keep in mind over here in this one, it was also coming out of the page, but just a reminder, they don't have anything to do with each other, okay? This electric field and this electric field are different. And so are this electric field and this electric field. I think I said electric field for these two, but I meant my magnetic field. Okay, so these ones are also different. So just because these two are going in the same direction does not mean that they are the same thing. So please keep that in mind and be careful about that. So that is how a mass spectrometer works, and that's how to do all the math with it. So again, there's my first chamber, which just accelerates it due to one electric field. And then we have my second chamber that's just going to select ions that are going certain velocities, that have a certain charge and a certain mass. Because if they have too much charge, they're either going to go up to the negative plate. If they have too little charge, then they're going to go down to the positive plate because of the magnetic force. So only certain ions can actually make it through here with certain amount of charge. So then we can just care about the mass or the charge to mass ratio in the third chamber. Okay, and again, that's only a magnetic field, and it's not the same one as the one that was before. And then we have our centripetal force here, and just remember, centripetal force is equal to mass times centripetal acceleration equaling v squared over r. Okay, so anything that you can be asked about a mass spectrometer, I've basically written down all the equations for you and all the combinations of the equations. You're welcome. Please study it. Please do a lot of questions on it. I hope I've covered everything. I hope I've answered all your questions. If not, let me know, comment, or just shoot me an email or something. Otherwise, I hope you guys are having a great day. See you later.